Hello, good morning. Can you hear me? Can you see me? Hopefully, yes.
Yes, yeah, I can confirm.
Yes.
Okay. Apologies for this 10-minute delay, but we had some connection issues that have now been resolved, at least partially and in a functional way. So let me welcome you all to the second training seminar of the acceleration program of SolarHub. Today's lecture is about solar thermochemistry, which is how to use solar heat generated from solar energy by concentrating solar technologies to drive chemical reactions of industrial importance. That's the general context, if I may say so. So today we have 4 presentations. We will start with an introduction to concentrating solar technologies. We will see some examples of, let's say, reactions of industrial importance. And the last presentation will be about solar hydrothermal liquefaction, which is directly related to redesign number 2 in the SolarHub project. So without further ado, let's start. Let me ask you on a practical note, let me ask you to use the chat to place comments and questions during the presentations. Normally, there is no provision for discussion after each presentation, but we may see how it goes and we may change this if needed. At the end of the session, there is a 30-minute discussion session, which we will exploit. So if you will have placed your comments and questions in the chat by that time, this is going to be very useful to trigger our discussions. Okay, let's start. The first presentation is by DLR, by Gökhan Mumin. It's going to be a general presentation of solar thermochemistry. Gökhan, the floor is yours.
All right, thanks a lot. Thanks for the introduction. Let me share my screen and also maybe activate the camera. Nicer. So I hope you can see and hear me well. If not, just let me know.
Yes, we can see you. We can also see the presentation.
All right.
You may proceed.
Good morning, everyone, again. So welcome to this training where I will basically introduce the CSP as a technology and talk a bit really shortly about some potential applications. And then the colleagues afterwards will go a bit deeper into these applications. So the title of the presentation is Solar Thermochemical Fuel and Commodity Production, Introduction and General Perspectives. Yeah, I'm Gökhan Mumin, since 8 years at DLR. I'm a chemical engineer. I did my PhD at DLR on solar cement production and currently a project and group leader. So I would like to talk in this presentation a bit about the theory of CSP. So where does everything come from? How did it start? What are the potentials and limitations, let's say? Then go over to electricity to heat transition. So CSP, while it's a technology directly producing heat, was mainly or is widely employed for electricity production. But it has applications or potentials beyond that. And this is also what we will talk today about. And then also I will mention some applications and show basically the broad range what CSP technology could provide, and showing the potentials in the future. Then let's dive into the theory. So concentrated solar thermal energy in its very basic form is basically the bundling of solar radiation. So everyone knows this from a magnifier, which I think fascinates every child once you experience that. So basically we take sunlight and focus it on a small spot. And this idea, I think there even from the Greeks some literature of focusing sunlight. This idea became always a technical challenge to pursue. And the first design in a relevant scale was then done by Augustin Mouchot at 1880 around. You can see here his design where sunlight is hitting the parabolic mirror and then is focused on this tube in the middle. And in this case, he made a design with 20 square meter of mirror area and produced steam at 6 atmosphere. Now, where are we currently with this technology? So these are the first steps, or these were the first steps 140 years ago. Currently, we have the biggest solar tower with 250 meter height, 1.2 million square meter of mirror area, and 660 megawatt thermal power, which is produced in this tower. And to put this into perspective, a cement plant, currently a cement plant at the upper end of the scale, like producing 10,000 ton per day of clinker of product, needs 440 megawatt thermal continuously. So we already see we are in the same magnitude. So of course the solar system can operate only 8 hours per day, but there are solutions to expand this to 24 hours. And we can see that, yes, we have a technology that can tackle some of the biggest industries' energy demand. Now, to understand a bit the limitations or also the possible applications of this technology, I would like to talk a bit about the relevance of the solar energy. So if you look at renewable energies, I think this is something that we should remind ourselves often, how vast the amount of sun energy is, or solar energy. So if you look here at the annual renewable energy potential, we see that the sun is way, way bigger than wind, which is then on the second place, biomass, then I guess geothermal heat, usable water power, and tides. So we should never underestimate this, I would say, how big of a potential this is, and how much of the sun energy is in that sense unused and could be used. If you compare it with total conventional energy sources, you can already imagine they don't stand a chance, basically. So the cold energy is maybe a bit more than the biomass energy, but definitely even lower than wind. Oil is definitely in the range of biomass, natural gas similarly, and uranium even lower. And of course, the important point here is now, what is our energy demand on Earth? It is this one. So the annual global primary energy demand is orders of magnitudes lower than what we receive basically from the sun. So this makes it, of course, a natural source to take the energy from. And why do we have to concentrate this energy, basically? So if we just look very briefly into theory, so we have the sun with a vast diameter with a surface temperature of 5,700 Kelvin, and a distance to the Earth is even bigger than this diameter. And what this leads to is that the sun rays that reach the sun are very diluted, actually. So the sun is very powerful, but the radiation coming from the sun is spread in such a way that what reaches the Earth is very diluted. This allows us obviously to have here livable temperatures on the surface, but also this means the direct sunlight we receive, which is at the maximum 1,367 watt per square meter, is not usable in itself for high temperature applications. And for this, you have to concentrate the sunlight. And the concentration of sunlight is defined by two quite simple factors, let's say. One is the surface area, the inlet surface of the concentrator. We can imagine this with the magnifier. So all the radiation entering here is concentrated on a spot, and this is indicated with A star, and this is the outlet surface of the concentrator. And this is then the ratio. So you can imagine if this one is 1,000 times smaller than this one, the concentration factor is 1,000 basically. And to perform these concentrations, we have two types or two categories of concentrators, which we call point focusing and line focusing systems. So point focusing systems are, I guess, more straightforward. So what we have here is sunlight and hitting the surface and then being concentrated on one point, on one spot, basically. So this one is a three-dimensional focusing. So all the radiation from the surface is focused then on one spot, ideally. The dish is therefore the ideal or gets as close as possible to the ideal concentrator, while a solar tower with a heliostat field indicated here is basically an approximation of this, because you can very hardly scale up such a dish system. But with a heliostat field, as I've shown before, you can have huge fields with very big towers. And there, again, you focus the sunlight on the absorber here and can use the energy. All right, so both of those are point focusing system, and line focusing systems, as their name already suggests, focus the sunlight on a line, basically. And this is the absorber here in the middle that we see. And yeah, the sunlight is then focused on this line, as I've said. And an approximation of this parabolic trough, parabolic mirror, are Fresnel mirrors, which are straight, and they approximate basically this curvature with single mirrors that are inclined, and they then focus the sunlight on the absorber again. Okay, if we again apply now this concentration factor that I've mentioned before, for that we have to observe in a bit more abstract way. So if we draw here the concentration line, let's say, this is where all the radiation hits the mirror. So this means in the solid gray line, all the radiation entering through the solid gray line from top is absorbed, and it's, if we assume it's absorbed on the spot, these are the two ratios of these areas, basically. If we watch this from the side, this is how it looks like. So we have the sunlight entering, and all that enters through the solid line is then focused on the spot. And this gives us, again, the concentration ratio. So all that enters through the solid line, hitting the dot here, this is the ratio we can achieve in a two-dimensional concentration, which is 215. This is the maximum we can have here. And mind you, here in this drawing, the sun rays are basically parallel. This is not really the case, which will lead to some reduction of this maximum value, but this is just as an orientation. And if we apply the same for the point focusing systems, again, taking the surface we have where all the radiation enters, and then the focused area, we have a concentration ratio of 46,200. And that already gives you a rough feeling that point focusing systems can achieve much higher temperatures than line focusing systems. Now, how do they correlate though, and how can we estimate this? And this is done basically with the equation shown here, where the temperature on the absorber is the temperature of the sun, and then the quadratic root, I guess, of the concentration ratio we calculated. And we can see for three-dimensional concentration and a concentration factor of 46,200, we could reach 5,500 degrees C, which is the surface temperature of the Earth, of the sun. And that's logical. So if you take the sun rays and they travel through space without losing any energy, then they enter the Earth atmosphere, and there you have some reduction of the energy. But if we neglect that, if you then focus it back basically to the same density as it was coming from the sun, then you reach the surface temperature of the sun. For the two-dimensional systems, we have this factor of 215, and there we can reach max temperatures of 1,235. Now, of course, these are I wrote it here, the theoretical limits to concentration. The practical limits to concentration look more like this. So due to technical limitations, because we cannot have an ideal mirror, and due to the non-parallelity of sun rays, it's not possible to focus them back on one point, actually. And that means we can only reach 3,600 degrees in practical cases for the three-dimensional case, and 970 degrees C for the two-dimensional cases. These are again only limits, because in this case, if you reach these temperatures, you basically did not consider any other efficiency, you did not consider any heat extraction from the system. And that means, yes, you can reach these temperatures, but they're practically or in a practical application not really relevant. So once you say we have certain efficiencies and certain losses because the system will heat up and it will lose also some of the energy, what you end up with in an example case here with 80% efficiencies like this. So you could reach in a solar tower system, let's say close to 2000 degrees C. If you have better systems, maybe even higher. And while in a two-dimensional case, the line focusing systems, you could reach 500 or even more, depending again on the efficiency of the system. So that's where we are operating to find the better systems to approach more this limit, let's say. But the good news is that these temperatures we see here, especially for the three-dimensional case, starting from 500 to, well, up to 2000, let's say, they are more than enough for the majority of industrial processes, as we will see later. But this is the background basically to CSP, its limits and how it's operating, let's say. And if we look at the real applications for line focusing systems, we have plants with around 400 degrees C, because the temperatures here, of course, they assume ideal heat transfer fluids and everything. So you really have to find the proper heat transfer fluid, proper building materials, which is also a challenge in itself. All right, so for line focusing, we can achieve around 400 degrees C, and generally one unit is in the size of 10 to 100 kilowatts. You can put them just in series, and then you can increase the power there, but just as a rough orientation. While for tower systems, we can achieve even above 1000 degrees C. This is currently limited to around 550 by the heat transfer fluid. This is exactly what I meant with what is the technology capable to do, and what are our, let's say, building materials and construction materials on Earth, let's say, currently we have, where we can really make use of the heat. Okay, so the temperature here is way higher, and also the power, you can see it's an order of magnitude. So no, 3 orders of magnitude. So it's in a megawatt scale. And as I've shown in the very beginning, the biggest solar tower currently has 660 megawatt thermal. Okay, this was all for the theory. So I would now continue a bit with the applications of CSP, which is, as I've said, currently mainly electricity production. But if you look at the heat demand, if you look at the energy distribution globally, you can see that the industry consumes about 32% of the primary energy. Out of that, 74% is heat. These are values from 2014, so I guess it improved a bit with the renewable energies, I hope. And out of those 74%, 30 is low temperature, 22 medium, and 48 is high temperature heat, which means 11% of the total primary energy demand is actually high temperature heat. And this is a significant number. So with CSP technology, as I've shown before, we can reach these temperatures. And the main question is what kind of design, what kind of receiver, and what kind of mirrors we use for the applications. Good, this was the intro to the heat aspect. As I've said, the current usage of CSP mainly is electricity production. How is that done? A very typical cycle, let's say. So we have the tower and receiver, we have a heliostat field, and in the receiver we circulate the heat transfer fluid. It is then stored in a hot tank, and here you can see it's around 560 degrees C. And from the hot tank, either it goes to the steam cycle, or it produces steam, let's say, for the turbine, and we produce electricity, or it can also just be kept in the tank. So overnight, we can also produce the steam. And this is actually where we draw the line between the solar system and the non-solar system or operation. So the left-hand side will operate 8 hours per day and collect the energy during the day and fill up the tank, while the right-hand side will operate 24/7 and then give away the energy to produce continuously the heat. And that's actually the main advantage of CSP. So we really have a easy to store media, and this can be used then continuously for electricity production. The status of CSP currently, so these numbers are from November 2023, looks like this. So you can see the highest number of installations in Spain, or the highest power, with 2.3 gigawatt. Then we have China now catching up a lot. So there's the red ones are under construction. So you can see 1 gigawatt is being built there, which will increase its number to 1.6. I see also MENA region has quite a high number, also with some significant installations. While we can see more in the Western hemisphere, let's say, that there are no new plants planned currently. But in total, we're talking about 8 gigawatt, which is either operational or under construction. And the types of the systems are distributed like this. So 74% of them are parabolic trough systems. So this line focusing systems, because especially for electricity production, this is quite, let's say, established technology. And we have 26% of solar tower system, which, to remind you again, can reach higher temperatures. So for heat applications, this is the ideal candidate, let's say, but we already see a first contradiction here, that the more mature technology or more applied technology is the parabolic trough, actually. And we see there a bit of a need to develop, especially the solar tower, for other applications. Now, I would like to talk about the electricity application now, and then transition with this to the heat application. So to give you a feeling why it is used for electricity, but why it's also very promising for heat usage. And for this, I would like to look at the cost of the electricity. So if you look at the levelized cost of electricity of renewable technologies, you can see this data from IRENA, where we have here biomass, geothermal, hydropower, PV. You can see a huge drop from 2010 to 2021. Onshore wind, offshore wind, and here is CSP. CSP also had a major drop, or a significant drop in the costs, but you can see that compared to all of the others, it's basically at the upper end of the cost. So just looking at this data, you would say CSP is the most expensive renewable electricity source. So why would we use it? And the question is this true in all cases? Like, what does this number really represent? And for this, you have to look at the capacity factors, like the hours of operation per year, actually. And if you look at the, let's say, other candidates, I would compare here with wind and PV only. So onshore wind, we can see that the capacity factor is up to 40% in the latest installations. And yeah, we have the drop in the cost here. PV reached only, let's say, 17%, which means you install the PV plant, and during the year, it only operates 17% of its capacity. So this is quite a significant or important aspect of it. And offshore wind reached 39%, so it was even higher in the past, it seems. But yeah, this is the status of those. And now you can already imagine that I've talked a lot about the storage and the positive aspect of CSP. CSP can reach way higher capacity factors. So let's say with relative easy or low effort, it can reach 30% or 35% in this range, which is almost or basically double of PV, and which competes directly with the wind technologies. But we can see the latest installation. This must be the plant in Chile, where we have one of the highest solar radiations. It achieves 80% of capacity factor, which is quite impressive. So for a renewable technology, except for a hydro, this is quite an achievement. Again, you can see that the cost in general dropped, but stayed at a relatively higher value. But that means exactly, or this is really crucial to understand this, that CSP can provide very high capacity factors, at least 2 times compared to PV, and this basically justifies or balances again this cost. And we will see this in the next chart. So if we look at the electricity cost versus storage duration, we have on the left-hand side here PV installations with batteries, and you can see basically a trend upwards. So if we just say, what is it here, it's 4 hours, then the cost basically increase by several factors. And you can guess the data here from the UAE is a CSP plant. And you can see that while CSP will look more expensive for PV without storage, it's clear that with storage, it's a very, very attractive solution. And that's the main reason also why CSP is employed for electricity, or mainly for electricity production, as also electricity is more expensive than heat. And I would just like to cite the IRENA study on this. So it says, although battery storage often grabs the headlines, given its rapid cost reduction, CSP and its low-cost thermal storage systems are often overlooked. And what they also say is, this is unfortunate, as CSP remains, along with pumped hydro storage, the only low-cost, long-duration storage option available today. And this is really something we have to keep in mind and really push this. Let's say that we have a technology that can store heat, as I've said, as I've shown before, at least fulfill 40% of the capacity, probably even more depending on the region, or even more. And we have to really convey this message and keep this in the minds, let's say. And now I would like to transition from the electricity we talked. So CSP has clearly an advantage on electricity if we consider the full load hours, the operational hours. But the question is, how does the technology compare concerning heat? Because heat is really the market where CSP, it has some installations, but it's not in a big way entered the market. And for this, I would like to talk about the learning curve trends. So if we just look at CSP, it's the purplish line, we can see with the installations, it dropped below $0.15 per kilowatt hour. And we can see again, the other technologies are cheaper. This is what we saw before. And PV also dropped quite significant. One important message here is that the inclination is actually the same. So if you would install more and more CSP, you would also reach these costs. So the technology itself shows a bit a high potential, let's say, for cost reductions. But to reach the same level as PV, again, this is without considering the storage, because if we consider the storage, CSP is already competitive. But to reach the same numbers, it would have to be scaled up by a factor of 6.5 and reach 40 gigawatt of installations. But the story is different for heat. And why is that? So we should be clear of that the primary use of concentrating sunlight is to produce heat. And if you look at a breakdown of the efficiencies of a CSP system, we can see that the heliostat field can achieve around 60-65% annual performance, receiver 85 to 87, power block for the electricity production then 40-45, and auxiliaries 90-95, depending on some different technologies we use there. Which means at total design point, we have 20.9 to 24.2, which is really the ideal operation point of the plant. And for the total annual operation, this drops a bit because we have to deal with transients, with clouds and everything. And the total annual of a CSP plant is then around 18 to 20.5%, which is comparable with PV. So PV for total annual also shows values of 15 to 20% maybe. So for CSP, we can say sun to electricity 18 to 21. But if we just consider sun to heat and say like, okay, we don't need a power block, this efficiency more than doubles actually. Because we don't use half of our energy in our power block and we make direct use of the heat. And this means if the efficiency is more than doubled, the cost is halved basically. So with the same installation, you produce double the output. But if we even consider that we have less components, so this was just the efficiency, but if we consider the costs that we also get rid of, then actually we end up with about 25% of cost. This is an estimation, maybe a third, but 25% I think is a safe number, which brings us then to this view. So concentrated solar thermal energy has basically a quarter of the price of CSP, and this is already competitive with PV, for example. And mind you, again, PV without a significant storage. So we again have a technology here with a significant storage, cheap storage, which is already competitive and I would say in the major regions cheaper than PV, and which is therefore worth to look at more and implement it more in processes. Another aspect I want to throw in the discussion is the land demand. So these are some data from 2013. They might have changed, but just to give another aspect of the discussion. So if you look at the land demand for PV installations, hectares and gigawatt hour per year, we can see that large PV installations require about 1.5 hectares. For CSP, parabolic trough or towers, this number is either similar or a bit lower. And you know what will come now? If we look at the heat usage, this is the number we get. Because basic technology is now double as efficient because we don't need that power block. We produce much more useful output. And basically the tower system for heat usage requires now less than half of what a PV installation needs. And this is another important aspect. And there are more factors you could take into play, like the CO2 footprint. PV installations currently have a higher CO2 footprint because of their production in China or mainly in China with coal energy. But there are some aspects that we really have to keep in mind and say like, okay, is this really the technology to go for, or are there more efficient and more direct ways of producing the heat we need for processes? So I would summarize until now what we discussed about or what I mentioned. So we have with concentrated solar energy, we have a technology with very high efficiency to generate renewable heat from the biggest renewable source, which is the sunlight. And it can reach temperatures above 1000 degrees C, I would say easily without, so already the research is going in this direction. And it is cheaper to store than electricity. This is a very important factor to keep in mind. And now I will shortly mention two sectors at promising applications. As I talked, other colleagues will go deeper into this today, a bit about fuel production and commodity production. So how can we make use of this heat that we produce by concentrating sunlight? And one application is the solar thermochemical fuel production. So I will start with the figure on the right-hand side. What we need for that is a reacting surface with specific components where water is getting in contact, then giving away the oxygen. Yeah, so we have here the oxygen, which is basically reacting here, and then leaving the reactor with the surface. And to have this release of oxygen, we have to cycle the temperatures, which I've indicated here. So at low temperature, this is what happens. The oxygen is captured on the surface, and at high temperature, the oxygen is released from the surface. And this is what we can make use of in thermochemical hydrogen production. Here you can see a reactor tested by DLR. So the water, or in this case, it's steam, is entering the system. It's getting in contact with the structure. You can see here a foam indicated. And afterwards, we have the product, which is the hydrogen. And then at the gas outlet, we have the components. Here you can see some tests we performed. So we have here some quite big installations with artificial lamps. So we imitate the sunlight to have really stable conditions. And you can see here the size of the receiver. You can see here one exemplary operation. And here again, a person to indicate the size of the whole system. Again, some close-up pictures here, and you can see here when the receiver is or the reactor is heated up. And in front, we have here a protection not to overheat other components. And inside, we have the reaction I've shown. Again, if we come back now to this drawing, so in the front we have a window here, so the gases, you have a controlled atmosphere, and you can see on the right-hand side that the lamp power in yellow is step-by-step increasing, so it's shown on the right-hand side, reaching, 140, 150 kilowatt. And we have the hydrogen mass flow in red, which is then starting. So once you heat it up, the oxygen is released. If you cool it down, the oxygen is taken up, and then you again increase the power, so the oxygen is released. So these are the blue lines. And here you can see an infrared picture of the surface. And below that, you can see the hydrogen yield per cycle and the reactor front temperature indicated at the spot 1, which is quite hard to measure. It's really at the highest temperature location at the front. But what we see here, based on the temperature, we see a bit distribution of the hydrogen yield in the process. Well, this means so we could use it at around, you see, 1,300 degrees C to produce hydrogen out of steam. This is one case to make use of this technology. Another big research area, I would say, are commodities, so except of fuels. And one typical or few typical usages there are metals. So in general, we can say that the need for metals is increasing. We can see here the aluminum production in 1,000 tons. And you see how, so the colors are different countries, but not relevant in this case. So we can see how the demand increased a lot, or the production increased a lot. Similar for copper. So for copper, we can see this kind of distribution. So we are now more here at 2020, and we expect even more to increase. Now, there is one paradox with metals or general ores or mining, is that the energy requirement is generally not decreasing with the time. So the industry cannot manage to reduce the energy even further. So it doesn't get more and more efficient. Why is that? Because the mines deplete and the best resources are already taken away. This is very typical for copper production. And the energy demand is actually increasing if you look closely. So really they have to treat more and more ores with lower grade quality to receive the same amount of copper, for example. And we all know what will happen if the electrification goes on and it becomes more widely in the industry implemented, then the need for copper will even more increase. And the point is that the recycling of those metals needs only less than 90% of the energy. So for aluminium or copper. But the recycling in both cases has a quite low share. And this is something that could be done easily with concentrated solar thermal energy. Another application I want to talk about is cement. So one of the most used commodities worldwide in volume are water and concrete. And concrete is made up of cement, which is basically the energy intensive component here. And probably this is known by many, but the cement production is responsible for up to 8% of the emissions, of the global CO2 emissions. And again, related to the outlook, the demand is expected to grow. So and in this study, they predict 23% increase until 2050. So with this, I mentioned some applications like metal recycling, but also the cement production process where the energy could be used. And now I want to show some tests we did at DLR, which are still on lab to pilot scale, let's say, but gave promising results. And one of them is the melting of aluminium. So we reached their temperatures up to 900 degrees C. You can see here the molten aluminum being poured. We did batch operation with approximately 20 kilograms of material at a time, and the heat input through radiation up to 18 kilowatt. Another case, this is now linked to the cement. So we calcined cement raw meal. Cement raw meal is the main component is calcium carbonate, reacting at 900 degrees C or above 900 to calcium oxide and CO2. And also this CO2 you have to capture. And this is also what we tried in a rotary kiln, solar heated rotary kiln. So we have calcium carbonate entering, fed into the reactor. The reactor is heated to 1,000 degrees C to have fast kinetics of the reaction. and the product leaves at the bottom, and CO2 can be extracted ideally at the top. And this is how it looks inside. So again, we have here in this case, it's a point focusing system, because otherwise you cannot reach these high temperatures. And it enters the reactor, and then the radiation diverges again after entering. And we have here the material that flows through the kiln and leaves it then. And generally, we differentiate here between the crucible, the red area, and the insulation, the purple area. What we did there was the calcination of cement raw meal of industrial grade, which is very fine as a material. We did tests with calcination rates up to 95% or even higher. We had a continuous mass flow of 4 to 12 kilogram per hour, which is still, of course, low compared to a cement plant, but showing the feasibility of this technology. And heat input through radiation was 14 kilowatt. And we also did investigations of mixing and heat input. And we are now pursuing also this, this research in a current project. So we want to calcine limestone itself only, the main reactant of the cement raw meal, and to feed the calcined limestone to the cement process. We plan a continuous operation of 40 to 95 kilogram per hour. You can see here a visualization in the simulator I've shown before. And we expect heat input of 50 to 100 kilowatt. And we want to separate the CO2 as pure as possible, because this is a significant amount of the limestone. It is actually 44% of the mass. And the trials are now planned for early 2025. So my last application or example is a calcination of kaolinite and halloysite. Again, some minerals that need thermal treatment. But in this case, they release water, and we treated those for the synthesis of zeolites, so nanofilters, which are widely used in detergents, as catalysts, in many, many applications. And we did tests in a temperature range of 600,000 degrees C. We did a batch operation of 1 kilogram of material for each test, and had heat input through radiation of 6 kilowatt. Okay, then I think I'm coming to the end of my time and also the slides. So I want to summarize that we could use the technology, and I've shown now some proof of concepts, more lab scale applications, but we can use it for a vast application where we can treat minerals. This is columenite is for boron, aluminum recycling, phosphate ore treatment, magnesium carbonate treatment, or limestone, or even higher for fuel applications. And why I'm saying is it's more than a vision, because if we now go back and say, like, where did the technology start? And it was by the work from Augustin Mouchot. He writes in his book, perhaps it is even possible to use this heat source, as Buffon already suggested, for the calcination of gypsum and limestone, or for the reduction of ores, which is exactly what we're looking at. But the great natural scientist feared that the bodies could cool down in the air at the focal point of his mirror during these experiments, but this can be prevented quite simply by placing the substances to be calcined in a glass cage, or even better, in a blackened metal container standing in the cage. So really designing an absorber that makes most of the energy coming into. And there I would like to add ore in a solarized reactor or rotary kiln that we are working on. And with this, thanks for your attention, and I'm looking forward for questions later then.
Okay, thank you, Gökhan. I think, and thank you also for keeping the time. This was really important. So I think as an introductory presentation, we got the point. We also saw some applications in your last slides, but now we will go deeper into this with the next presentation, with the 3 next presentations actually. But for the first one, it's going to be Matthias Payne from DLR about thermochemical energy storage. So Gökhan already highlighted the importance of storage and how this can be a game changer for solar thermal. And Matthias now will provide some more information on that. So Matthias, the floor is yours. And may I also remind you to use and encourage you to use the chat for any questions or comments during the presentations. Matthias.
Yes, I'm setting up the presentation.
We can see it, yes.
Okay, I'll turn on my camera as well, so you can see me.
Yes, we can see you.
Okay, great. So yeah, welcome everyone. Also from my side, my name is Matthias Pein. I'm just as Gökhan, working in the Institute of Future Fuels here at DLR in Cologne. And I will present to you the general concept and also like recent developments in terms of thermal and thermochemical energy storage, which can be used, as was already introduced to you, to prolong the use time and uptime of concentrated solar thermal power plants, but also in a mean to utilize renewable electricity from other sources and use the power of thermal storage in that sense. So why are we even considering high temperature thermal energy with storage devices? So here you can see the high temperature heat demand of the three of the biggest industries globally. So the chemical industry, steel production, and cement production, where you can see, or where I would like to highlight that for the heat demand of the production is the biggest emission or biggest source of CO2 emissions. So to decarbonize the heat provision for these processes is crucial to reduce the CO2 emissions of these heavy industries. You can also see, for example, in the cement production, where one of the biggest factor is that the process itself actually releases CO2, but it was already mentioned that capturing the CO2 and utilizing it is one way to reduce these emissions. But to reduce the emissions that come from heat supply, we need to decarbonize that, and for that, mainly we need to have reliable and also readily 24/7 available heat supply for the industry, because most of these processes are running 24/7 in a factory and they cannot be interrupted just because the sun is not shining anymore. So we need to have reliable storage for high temperature heat, which makes it feasible to run these processes essentially in a 24-hour operation. So what has been done in the past is mostly to introduce sensible heat recovery systems. So most of the heat supply right now in industry is coming from fossil fuels, so mostly methane gas that has been burned. And the hot flue gases can be captured or can be led through a sensible heat storage, so-called copper stoves, which are essentially like fire bricks, which you can see here. So you basically have like these bricks that come with flowable channels. So there's gases able to pass through these. You can basically stack them. This is mostly, so originally this has been concrete, but it can also be like other waste and debris, ceramics, high temperature ceramics, mostly inert. So this is only a means of sensible energy storage. And this is also already incorporated in many CSP plants, such as the solar tower that we operate at DLR in Jülich. So there's a thermal storage which can store heat up to 6 hours, I believe, which is made out of inert material that does not react with the heat transfer fluid, but is only storing the heat sensibly. On the other hand, One could also think to utilize such heat storages to store excess electricity from renewable sources such as wind or PV. So utilizing electric heaters to heat up such storages and make the power available basically on demand, and taking away a bit of this volatility of renewable energy sources such as PV and wind, and be able to supply power or heat to the industry on demand. And there are big players involved as well, such as Siemens, who are working on big storage mediums and big storages to make these industrial processes more feasible, and to supply heat and power on demand, instead of basically only when the sun is shining or when the wind is blowing. And most of these work or this work has been done with readily available materials such as aluminum oxide, cement, bricks made out of waste of construction. So that's one easy way to access inert or sensible heat storage media. But I want to highlight the fact that the specific heat capacity of such storage devices is limited, because you can only store heat in a sensible fashion. So there's no chemical reaction involved. So basically the specific heat capacity is somewhat somewhat limited to the amount of heat that you can store in the crystal lattice of the materials, which is in the range of about 1 kilojoule per kilogram Kelvin. However, when you look at costs, but also about volume, to increase this heat capacity is crucial to allow for bigger scaled up systems. As we've seen, the heat demand is huge, and the availability of large scale tower systems is also increasing. So the bigger the concentrated solar energy plant is, the bigger the storage system has to be, especially when you want to increase the amount of storage time, maybe even beyond 24 hours, to account for days where maybe the capacity cannot run at full power. You can cover, in the best case, even multiple days or weeks of shortages of concentrated or solar radiation in that sense. So what is the solution to that, in order to increase the heat capacity of such a storage medium? Because the general concept is rather easy. You have bricks, you put it in an isolated container, and you heat them up. You pass air through, or any other residue gases or flue gases, to heat it up. And when you want to extract the heat, you take again a gaseous heat transfer fluid, pass it through these open pores or channeled bricks to extract the heat again. So what the biggest challenge is to increase the heat capacity and the thermal resistivity in order to be able to supply heat at higher temperatures, but also to increase the capacity of the storage medium to be able to have a higher capacity at a smaller volume, to be able to scale up these storage systems to a mega or gigawatt scale. So essentially, as already mentioned, rocks and bricks and sand and slag, these things have been used or are used as sensible heat storage media. They're cheap and they're easy to use. On the other hand, metal oxides that are redox active, so where there is a chemical component or chemical reaction adding to the sensible only heat storage or heat capacity, can provide a better efficiency, but they can also provide a much higher capacity in the range of like 30% higher CP compared to inert ceramics or sensible only storage devices. So this concept is like commonly called breathing bricks. So these bricks are breathing air. Essentially, when you heat them up, they release oxygen and in an endothermal reaction, and they save this this additional energy in the crystal structure or as a chemical potential. And then when cooling down, they take up this oxygen again, so they inhale the oxygen again. And this reaction is an exothermal reaction, so in that sense, the heat is released again. So with that, utilizing air as probably the easiest to handle heat transfer fluid, one can utilize this reaction to increase the heat capacity. But we can also do other things with that. So you can combine heat storage with other reactions. And I just brought here like an overview of the reactions that could be done with such metal oxides in redox reactions with metal oxides in a thermochemical sense. So a large fraction is the fuel production, which will be covered in a later presentation as well. So I'd like to focus on these bottom parts, which typically happen at temperatures around 1,000 degrees and lower. So that's energy storage, heat storage, basically. You can also perform methane reforming, which is quite interesting when you look at the utilization of biogases or upgrading of biogases to hydrogen to make it available for synthetic fuel production. But you can also operate such a device in a way to separate air, because during the heat up, these materials essentially release pure oxygen. And when you then cool them down or during the extraction of the heat, it absorbs oxygen again. So one is able, with clever process design, to operate these devices as an air separation device where you can produce pure or highly pure nitrogen, which is a crucial source for the production of ammonia and for the product, like in agriculture, this ammonia is a crucial chemical to be utilized, and right now it's produced with high energy intensity cryogenic air separation. So this is a means of having a double use of such storage devices. But I will focus on the thermochemical energy storage, where you have a reduction reaction where heat is absorbed. So it's an endothermal reaction, oxygen is released. There's I will skip the water and carbon dioxide splitting reactions because I believe it will be covered later on as well. But for the oxidation reaction, then the metal oxide is again absorbing the oxygen and it's releasing the heat. So in that sense, you have a net effect of solar energy, which is converted into chemical energy, and then you have this heat available basically on demand when you want to use it, even if the sun is not shining. And that concept is called thermochemical energy storage, where you have a chemical reaction adding to the storage capacity. But always keep in mind that these materials, being solids, naturally have a sensible fraction of heat storage, which is still the largest part of the storage capacity. So when you break it down, it's about in the range of 70% of the overall storage capacity is still sensible, and then just the 30% of extra energy that you can store is then stored as chemical potential. But yeah, and then if you want to use it, you can run these storage devices also as air separation units. So in the past, there has been a lot of work, mainly on stoichiometric or so-called stoichiometric metal oxides, such as cobalt oxide, iron oxide, manganese oxide, because they reduce and oxidize at a distinct temperature. So you're able to keep the heat as long as the reaction is going at a certain temperature level. So in the project Restructure, which was an EU-funded project a couple of years ago, led by CERTH and DLR, there was cobalt oxide considered as a storage material in the forms of honeycombs. In the smaller scale, it was demonstrated that it works perfectly fine to store and release the heat again. And even in a bigger scale, with a storage device that was utilized in the solar tower in Jülich, with about 88 kilograms of cobalt oxide within. In the end, however, coated cordiorite honeycombs were used, and I'll come to that just in a couple of minutes to explain to you what the issue is with these stoichiometric metal oxides. Despite being highly efficient, they suffer from other drawbacks when it comes to shaping and making use of actual three-dimensional structures made entirely out of these materials. So you can see here, basically what's shown here is the temperature at different points of the reactor. So I want to focus your view here on these. This is the in the middle of the reactor system, where during the heat up, there's a certain point where the material or the storage device will keep the temperature. This is exactly the reduction temperature of the cobalt oxide. And then it will heat up again. So as soon as all of the material has reacted and is reduced up to the operating temperature of the maximum operating temperature, and then during cool down, you see this plateau here, where essentially the material will start to oxidize and release heat. So even although heat is extracted from the device, the temperature level will stay the same because the material is oxidized and releasing the chemical energy stored within as heat. But what are the issues of cobalt? Right? So for and other stoichiometric oxide in that sense, but especially cobalt oxide is quite expensive. It's a critical element, which in the past also has been utilized, or the demand has been increasing because it's also used in battery electrodes. But it's also potentially health harmful. So it's a toxic element, or the cations are toxic. And furthermore, it degrades very quickly during cycling. So these materials in such energy storage or thermal storage devices, they need to be able to withstand a huge amount of cycles, because whenever you charge and discharge such a storage device, there's a large temperature gradient that has to be covered. So in the range of 1,200 degrees down to 600 degrees for a charging and discharging cycle. And this over 100, 1,000, 2,000, or even more cycles, because you can imagine if you have tons of material in such a storage device, you don't want to change it every couple of days because it's been degrading. So it's very crucial that these materials are withstanding thousands of cycles without a lot of degradation. But as you can see here, after just 100 cycles, you essentially end up with a crumbled piece. And here you can see a picture of a extruded honeycomb, which after 51 cycles is no longer to be recognized as such. And the reason for that lies in the fact that due to doing the reduction and oxidation, the crystal structure of the material changes significantly, and which goes hand in hand with a thermal expansion within each cycle. So each reduction and oxidation cycle leads to a permanent expansion of the material, and in that sense also of any device that's made of this material, be it a honeycomb, a brick, or a bar. They all show the same problems, which will, in three-dimensional shape objects, will lead to cracking, and basically to a huge degradation of such devices or such components. And the same is also true for other stoichiometric redox oxides, such as manganese or iron oxide. Although being in a having a lower expansion per cycle, they still suffer from the same issue. So eventually they will degrade much faster than non-stoichiometric oxides, which such as calcium manganese oxide, which is a perovskite material, and I will introduce you to the class of material, the material class of perovskites in just a couple of seconds. But I want to draw your attention to the length change here per cycle. So these materials have been, or these samples have been cycled between 300 and 1100 degrees Celsius with 5 degrees per minute heating rate. And you can see after each cycle, the material comes back to its original size and length. So there's literally zero permanent expansion per cycle, which means the degradation is much less than in stoichiometric oxides. So it's the whole expansion and contraction, although there is an expansion and during heat up, and there is a contraction during cool down, this is completely reversible, which makes it much easier to have complex shaped structures made entirely out of these materials without degradation per cycle. So in our institute, we try to cover the whole process from materials development to components and shaping out of these materials and implementing these in larger systems. But since I am a material scientist and my focus or my line of work is mostly related to the development of materials and the shaping of the components, less so the implementation on a system scale, I'll speak a bit more about the materials and the components here in the following slides. So as already mentioned, the principle of non-stoichiometric redox oxides led us in the past years to the perovskite material class. It's essentially a multi-cation oxide, which can be it's essentially a material class that is defined by its crystal structure. So there's a certain crystal structure that defines a material to be a perovskite, and containing two or more cations. And you can see there's a multitude of different combinations you can choose from, or you can design with different thermodynamic and kinetic characteristics. So there's a huge playground where you can essentially design a material to your liking. And I could talk hours just on this material class, but I will not bore you with that. But just so you've heard the name, because most of the materials the components that I will show in the following slides are made out of such a perovskite material class, which has the beauty of being reduced and reoxidized in a non-stoichiometric fashion, so it doesn't change the crystal structure significantly during reduction and oxidation, which leads to the reversible or fully reversible expansion and contraction during cycling. Okay, but now having this huge playground available with the perovskite material class, we need to also consider the criticality of the containing elements. So we need to be, on a techno-economic point of view, we need to be competitive with commonly available, sensible storage devices in order to actually outperform them, not only on a technological level, but also on a cost level. So criticality plays an important role in the design of such materials. So we're looking for abundant and naturally also non-toxic elements that are cheap in their raw materials. One aspect that has in the past months and years rising to higher attention is also the topic of supply and monopoly. So if only a certain company or a certain country is the only supplier of a certain element, this is it's crucial, or it's critical to be able to have multiple supply routes in order to scale up such devices and ensure supply for production. So we have found in our past work that for thermochemical energy storage, essentially perovskites have the highest potential, and especially those made from manganese, calcium, and strontium on the one side in the crystal lattice, and titanium, manganese, and iron and aluminum are essentially most promising. As you can see, so the more in this scale here on this periodic system, the more blue an element is shown, the more readily available it is. So the availability is high in the Earth crust, and all of these materials I've mentioned just are essentially on the blue side here. So they are abundant, and no issues are there with criticality. So you can tune also these materials, and with doping, playing around with the composition. And I just want to briefly show you the impact of such a doping of these compositions. So here, that's a calcium manganese oxide. What you see here on screen is the thermal expansion. Again, in air, but also in lower oxygen concentrations or lower oxygen environments. Where you can see in air the expansion and contraction is perfectly reversible for each of these compositions, but under reduced oxygen atmosphere, for the pure calcium manganese oxide, there still is a permanent expansion per cycle. But this can be reduced, if not even diminished, by adding a small amount of strontium to the composition, where you can see there's a significant decrease in this permanent expansion per cycle, and also this permanent expansion can be reversed by cycling this component one time at higher oxygen concentrations, such as air. So this is more important for other applications, since the most use cases for thermal energy storage are utilizing air as a heat transfer fluid. So now, we have a material class that has high potential, but what do we do out of it, like to bring it back from away from the materials design or the smaller scale? We need to shape it. We need to make components out of it. And the choice of structure is rather important and needs to be adjusted to the type of reactor system. So out of the raw material, which is typically in a powder fashion, so you produce powders out of these ceramic materials or metal oxide materials, and with that you can do essentially whatever you like. if you know how to do it. So you can produce particles, bigger granules, porous structures, monolithic structures such as foams and honeycombs. And it needs to be a combination of the fitting reactor system and the proper structure that you're using in order to maximize the efficiency. So you could use particles and granules in moving bed reactors. You could use powders and fluidized bed reactors. Non-moving bed reactors are could be used with granules, but also with porous structures. And the benefits of open porous structures over particles, especially in non-moving bed reactors, such as the thermal storage devices, because these are essentially devices that are located next to the thermal energy plant, to the CSE plant, and you don't want to move it around, right? You don't want to move hot particles or hot materials, but you want to move gases, which makes it much easier to supply the heat to the industry, but also to produce electricity from it. So these porous structures have the benefit of a lower pressure drop at the entry of such reactor systems, and also allow for, in that sense, also allow for pressurized operation. So we believe that the porous structures have a large potential here, but the difficulty is in finding proper production pathways to produce these porous monolithic structures, and to ensure that they are rigid, that they are stable, and that they do not degrade with high amounts of cycles. So you can see some examples of smaller lab scale foams that we have produced made from calcium manganese oxide, through a way of reticulate, or in a way of the replica method, where you dip a polyurethane foam into a slurry, dry it, burn it off, and what you get out is a replica of the original polymer foam. And with that, we were quite successful in producing different shapes, different sizes, different porosity levels out of these perovskite materials, and a few of these examples you see on screen. On the other hand, I also mentioned honeycombs, and these are typically produced via extrusion, where you can take the same raw material, so the same powder, combine it with a binder and some lubricants to produce a paste that can be extruded into such honeycombs and dried and sintered. And these ones have been produced by our partners at CERTH. So the next steps towards upscaling would be to produce bigger components to ensure that they are stable and rigid, and withstand a large amount of cycles, and also to demonstrate their use in the field. So the next step would be utilizing these monolithic structures in a bigger reactor scale. Looking at the time, I conclude with to summarize the concept of thermal and thermochemical, or especially thermochemical energy storage, which is the utilization of redox oxides or metal oxides that are reduced during heat up, release oxygen in an endothermal reaction, and thereby increasing the heat capacity available. And then during the cool down, oxygen is absorbed again in an exothermal reaction, the oxidation reaction, and the heat is released again. So in that sense, we can utilize, or we can store process heat, we can store solar heat, or heat from excess renewable electricity to be made available on demand, which can then either be used as process heat for heavy industry, or to produce electricity on demand, to cover up for volatility of renewable energy sources. And in a real world application, so that's just a schematic here, these devices are also very flexible. So they essentially don't care where the hot heat transfer fluid or the hot air is coming from, right? So in an industry park, you could have multiple sources of heat that that are supplying this storage device, and combine it and increase or max out the efficiency of such a storage device. So you can have a solar tower available that charges such a storage device, but you could also, like right next to it, having a heavy industry plant that produces hot flue gases within their process, so they could charge up this storage device just as well. And during discharge, it could also be utilized. Very flexible, and basically on demand. So here's also just a nice picture of a larger foam structure, and finally, I would like to acknowledge these two projects where a lot of the work has been done in the past year at DLR. If you want to know a bit more about this kind of work or thermochemical energy storage, I can recommend to check out the websites. Big thanks also to our colleagues at CERTH, where a lot of this recent work has been advanced within cooperation together with them. And if you have any questions, I'm happy to answer them, and thank you for your attention.
Thank you, Matthias. Thank you for this very interesting presentation. I think we got a pretty nice overview of what thermochemical energy storage is, what are the advantages, the current status. Very interesting, and many challenges still to be resolved, but that's why we are here. Now, according to schedule, we are a bit behind, but this is mostly due to the late start of the event. So we will keep the program. We have a 10-minute break, and we will be back in 10 minutes. This means 11:44 or 11:40. Let's make it 11:45 Greek time, or 10:45 Central European time. Before starting the break, let me remind you that you can use the Q&A and chat functions to make comments and throw questions for the presenters. At the end, we will have a short discussion section. So see you in approximately 10 minutes. Okay?
हेलो
तब से बंद हो गया, बाहर गए तब से वॉइस।
चलो उसने देखता हूँ। हेलो
Hello, we are currently having a break. We'll be back in 5 minutes.
okay, I was wondering like what happened, so okay,
No,
great,
no,
great.
it's okay.
Okay,
So in
thank you.
5 minutes we'll continue. Welcome.
Yeah, okay, thank you.
Okay, hello again. The break is over. We can now resume. So the second part of the event, we switch from DLR to CERTH. The first presentation is by my colleague, Dr. Susanna Lorenzo. It will be about solar thermochemical redox water and carbon dioxide splitting cycles using redox schemes. So, Susanna, if you want. Presentation is already shared. I hope you can see it. If you don't see it, please speak up.
Well, hello from me. I think that now you can see the presentation in full mode. So, as Yorgos said, I'm working at the Artemis Laboratory in the Center for Research and Technology, Hellas, and have been involved in solar research and solar technologies, and more specifically in production of solar fuels, hydrogen, and syngas from solar thermochemical processes. And in today's presentation, I will give you an idea of the work that is taking place and progress, and as well as the challenges in this part of the solar research. You have heard in the previous part of today's event about solar energy and concentrated solar technologies, as well as the effort that is given in storing solar energy for use in for using solar energy in other areas or in the night and avoid temporal and local limitations. And there are also several other reasons that trigger the research around solar energy and in general alternative energy sources, and that have to do with the price volatility of fossil fuels and the overall effort of the industrial sector in greening the industrial processes, as well as the effort to limit greenhouse gas emissions. So we target alternative energy sources for the production of fuels. And in order to avoid the disadvantages that the intermediate character of alternative energy sources, and especially of solar energy, have, as well as I said before, the limitations that we have in time and availability of solar energy during the day, and also local limitations. So in order to store solar energy, you have seen in the previous presentations that there are means of storing solar energy in a form of thermal storage or thermochemical storage. And I'm going to speak now about solar-driven thermochemical processes for the production of solar fuels, for the production of hydrogen, syngas, and other fuels and chemicals that can derive from these initial two elements. The research around the production of solar fuels and the production of hydrogen mainly was initiated more than 40 years, 50 years or 60 years ago. And it was promoted mainly by research from the nuclear energy sector for using the high amounts of thermal energy for the production of hydrogen. Now, the aim was to find thermochemical reactions, thermochemical cycles that could that would have favorable thermodynamics for the production of hydrogen, since the direct thermolysis of water to produce hydrogen requires very high temperatures that are not appropriate for most materials that can be used for the reactors and the facility. So research was focused in finding these thermochemical cycles that could operate at temperatures that are appropriate for most materials. And there were more than 200 thermochemical cycles that were investigated that were characterized from different steps, two-step cycles, three-step cycles, or even higher, 4, 5, 6-step cycles that would involve different reactions that could facilitate the splitting of water mainly, and at temperatures that were below the thermolysis required temperatures of 2000 degrees Celsius. And this research has focused in several criteria that were derived that were related to the number of steps that would be needed for the reactions to take place, the number of the separations that would be needed. For example, if we would need to separate a solid from another solid, or a liquid from a liquid, this would increase the difficulty of the process. The number of elements that are used, or the abundance of chemicals that are used in the reactions. The need to use corrosive or non-corrosive chemicals, as well as the need to move parts of the materials for the reactions to take place. So these were the main criteria that needed to be taken into account in order to end up with the most appropriate and favorable reactions. So one of the most simple reactions that thermochemical cycles that can be used for the splitting of water or the splitting of carbon dioxide. It can be the same cycle can be used, are the two-step redox thermochemical cycles. You have heard about these cycles in the previous two presentations, and now I will show you in more detail what are these cycles have to do about. And actually, they consist of two different steps that are performed in two different temperature areas, regions. And in the first step, we have the reduction step of a metal oxide, a multivalent metal oxide, where in this step, the oxygen of the metal oxide is released, leaving the metal oxide with in a reduced state with oxygen vacancies formed in its lattice. While the second step, the splitting step, either the splitting of water or the splitting of carbon dioxide, is performed at lower temperatures. And in this step, we have the oxidation of the reduced metal oxide from water or carbon dioxide, where the oxygen is removed from water and carbon dioxide to fill in the empty space, the empty sites on the metal oxide, and produce at this step hydrogen and carbon monoxide. In this two-step redox thermochemical cycles, the metal oxides that have been investigated can be categorized in two different categories, volatiles and non-volatiles. In the volatile cycles and the volatile metal oxides, we have reactions the thermal reduction and the splitting reactions are taking place between the reduced metal and its oxidized form, the metal oxide. In the volatile cycles, in the volatile process, the problem is that there may be a case where we have a recombination of the products, so the metal that is produced and the oxides, and there will be a problem of separating the oxygen that is produced and the other products from the solid state. In order to avoid this separation issue, the non-volatile cycles can give the solution. Here we have metal oxides that remain in the solid state during the whole process, the whole duration of the thermal reduction and the splitting. In these cycles, we have investigated mainly ferrites that are iron oxide doped with other metals, zinc, manganese, cobalt, or nickel. Also cerium-based oxides that can be doped with zirconium or other metals. Perovskites that are mainly lanthanide oxides doped with other metals, as well as hertinite, which is a mixture of iron and aluminum oxide, or cobalt iron aluminum oxide. So in this case, I will from now on talk specifically about the non-volatile cycles and the metal oxides that remain in solid state. So focusing on the metal oxide, we have the exchange of oxygen from the gas phase to the solid phase. In the case of the reduction step, as I said, we have release of oxygen from the metal oxide at high temperatures and inert atmosphere. And during the oxidation, we have removal of oxygen from water or from carbon dioxide, and oxidation of the metal oxide with the oxygen going and filling up the empty oxygen sites on the metal oxide. You can see in the diagram on your right, typical evolution profiles of the products of hydrogen and carbon monoxide during the water splitting and carbon dioxide splitting, as well as oxygen that is released during the thermal reduction of the metal oxide. The curves are typical. They have there are peaks that reach up to concentration of the product, and then they are reduced, decreased down to a value. This curve, this type of curve, actually is related to the filling up of the oxygen vacancies on the metal oxide. So we have a decrease in the production of hydrogen and carbon monoxide as with the filling up of the vacancies. And this indicates actually the oxidation of the metal oxide. And this is a reaction that happens mainly on the surface of the metal oxide, while the thermal reduction of the metal oxide is happening throughout the whole bulk of the metal and not only on the surface. So the production of hydrogen and carbon monoxide and are it is very important to ensure that we have a high surface area. So we see that since the production of hydrogen and carbon monoxide is really happening close to the surface of the metal oxide, we need to ensure that we increase the surface area, and we have a very high surface area in a limited or very defined volume or space that will be available at the end in the reactor. And for this reason, there are different approaches, either from the particle side, so having reactors that use particles in high dispersion, or having reactors that are can secure high surface area using structures that have either channels like the honeycomb structures that can be either coated or extruded, or foam structures that have high porosity and a random pore structure with a high number of pores that can allow a high surface area. Or relatively new research is done in the last years on lattices that somehow combine the strict alignment of a honeycomb structure with the more random structure of the pores of a foam in order to enable an even higher surface area in the same volume of a structure. And in all these different approaches, we are working on the scale of hundreds of nanometers to micrometers for the case of powders and their use in reactors. While in the case of the monolithic structures, we are dealing with higher sizes, hundreds of micrometers for the case of the coatings and the channels, channel wall thickness of the structures, up to centimeters. Now, I will show you a few examples of use of these structures in mainly in the research for water splitting and production of hydrogen. For example, the research starts at the lab in laboratory scale reactors and comparing different structures or different materials, redox materials, metal oxides, for the production of hydrogen. You can see here an example of foams that are coated with nickel ferrite or cerium oxide. And on the diagram on your right, there is the production of hydrogen and oxygen during consecutive cycles of water splitting and thermal reduction. As you can see, there is a difference in the profile of hydrogen. In the case of the nickel ferrite coated foam and the cerium coated foam, this difference has to do with the faster kinetics of the material, the cerium oxide, compared to the nickel ferrite. We see that both materials are active, but there is a difference in the hydrogen production rate and how the kinetics of the reaction take place for these two different materials. Another example is structures that have been tested for assessing the durability, and under multiple consecutive splitting cycles, again in small scale at the lab or under simulated conditions using a solar simulator. On the left, there is the assessment, the evaluation of honeycomb structures consisting entirely of nickel ferrite that has been assessed during 600 cycles of water splitting and thermal reduction mainly to evaluate its durability under stress for long-term thermal reduction and long-term exposure under oxidizing and reducing conditions and high temperature. On the other hand, we have the production of carbon monoxide from CO2 splitting, multiple cycles that were performed on a serum oxide foam reactor exposed in a solar simulator facility where we have, I think, almost 500 cycles achieved, consecutive cycles achieved in this research. Now, as I said before, the materials, the metal oxides, have to be included in a reactor in order to be used for the solar thermochemical redox cycles. There are different reactors that have been investigated, mainly related to particle and to particles and structured reactors. These reactors are categorized based on the approach that is used for heating up the active redox phase, the active material. So there are particle and aerosol reactors such as fluidized bed reactors, vortex reactors, cavity reactors, as well as packed bed particle reactors that are directly irradiated, which means that they have a window, and through the window, concentrated solar energy enters to heat the metal oxides, to heat the particles. We have also indirectly irradiated particle reactors where, again, the solar energy enters through an aperture and hits an alumina tube or a ceramic vessel, and which is heated and indirectly heats the particles that flow inside the reactor. On the other hand, we have the structured reactors, where we have different structures. We have, as I said before, the foams, the monoliths, the lattices that are actually embodied inside a reactor cavity, and they form the main reactor core body. These are either directly irradiated, again, we have an aperture with a window and the solar rays entering the cavity and heating up the active redox structured materials. Or on the other hand, we have, again, structured reactors, but indirectly heated, which always involves ceramic structures, ceramic vessels, or ceramic tubes that contain the active redox material and the active redox structures inside, and which are indirectly heated with the heat to be transferred through the reactor cell. So all these reactors have been tested in different laboratories worldwide. And I am showing here only some examples that have been tested in either at small scale or in higher scale, pilot scale, with the aid of solar simulators. You can see here examples from smaller scale and for the evaluation of nickel ferrite structures in indirectly heated reactors, or cerium oxide foam structures in cavity directly heated reactors, or again in higher scale, pilot scale at the high flux solar simulator in Jülich for the case of directly heated cavity reactors. You have seen this example in the previous presentation, also from Matthias Pine. And also another reactor, which is completely different from the three examples that I have presented here, the particle packed bed reactor that has been tested in Sandia. All these reactors have been tested either for combined water and CO2 splitting for hydrogen and carbon monoxide production, or for just for water splitting. So in order to scale up, to move on and scale up and go up to the demonstration scale on an actual solar platform, there are specific needs for the reactor, and I'm just going to show you here an example of the hydrosol reactor that has been used in the previous projects in Hydrosol Beyond and Hydrosol Plant. You can see here the full reactor with the secondary concentrator and the reactor vessel. And in more detail, you can see the main blocks that are the metal oxide, consist of the metal oxide, the active redox material that is used for the splitting of, in the hydrosol case, the splitting of water, and how these are structured in a cavity that is included inside the reactor vessel, as well as some critical components of the reactor, which is the secondary concentrator and the quartz window, and how these are put on a solar platform for the test in real environment. These here are two examples of actual experiments that have taken place and actual experimental campaigns and demonstration campaigns that have taken place in the past in two different solar platforms. The case on your left is the sun-to-liquid demonstration campaigns on the solar platform at Indea in Spain, where the solar reactor consisted of cerium oxide foams. And you can see here an example of hydrogen and carbon monoxide produced during this demonstration campaign. And on your right, you can see the hydrosol solar platform at the Plataforma Solar de Almeria in Spain, and an example of hydrogen production during one day of operation on the solar platform on a reactor that consisted of nickel ferrite coated foams. In both these cases, we had reactors that were cavity reactors directly heated from concentrated solar radiation. All this research has led to several conclusions that included considerations and about the challenges, and not only the successful production of the successful splitting of water or carbon dioxide, but also the challenges that these technologies have that are related to the active redox component, and the strategy of heating and cooling of the reactor, and how you manage the concentrated solar radiation and the optical components and the heliostat field to achieve this strategy, best performing strategy. Also, challenges that are related to the reactor design and how to achieve temperature and flow homogeneity, as well as how to be able to exploit the parasitic losses that are in these processes can be identified, such as the use of inert gas and heat losses in order to enhance the efficiency of the process. While also the case of maintenance needs on the solar platform are also very important. And finally, the actual cost that is mainly identified to derive from the heliostat field, as well as the solar reactors. So in the case of the materials, we have identified certain challenges that have to do with as I said before, the enhancement of the contact of the reactants with the active redox material, and how to achieve higher surface area and better contact in order not to have the reaction taking place just superficially on the surface of the metal oxide, but also entering deeper into the bulk, and in this way exploiting the whole mass of the material that is used in the reactor, and not only a thin layer on the surface of the metal oxide. Also, another issue is the durability of materials and the structural stability. This was also mentioned in the previous presentation, but it is something that is very important to achieve material structures or material formulations that can be durable during multiple thermal reduction and splitting cycles, which means that they have to be durable under stress, under high temperature conditions, very high temperature conditions, and oscillation between very high and lower temperatures, and also under reducing and oxidizing conditions, which may affect both the mechanical strength of the structure as well as the material itself, since we can identify heavy sintering of the material or grain growth, which minimizes the surface area, the active surface area of the material, and as a result, the production of the final products and the efficiency of the process. On the other hand, we have outside the reactor, we have in critical points of the reactor, we have several issues that we could identify specifically for directly radiated cavity reactors, where we have the optics of the reactor that play a significant role, so that the concentrated solar radiation is further focused inside the cavity, and we achieve the temperatures that are needed for the reaction by exploiting the maximum of the available solar energy from the field, concentrated solar energy that we get from the field. So the optics are affected by the operation, during the operation of the reactors, and this is a challenge that needs to be dealt so that we can secure safe and maximum operation of the reactor. Also, there are other critical challenges, such as the sealing, achieving the sealing at high temperatures, temperatures beyond 1000 degrees Celsius, and between different materials. So we have to achieve sealing between glass and quartz and ceramic and metal parts. And this is a challenge that is always needs to be dealt during long-term operation of such reactors under realistic conditions in the real environment of the solar platform. While, as I said before, we have to exploit the waste heat, the heat losses that we have in such high temperatures, and achieve maximum recovery of heat from such processes, which would highly improve the process efficiency. So in the future, in order to deal with all these challenges that have been identified, we need to readdress revisit the design of materials, new materials formulations that are based on the old concepts, but are further enhanced with doping, such as the doping of cerium oxides, or the investigation of different formulations of perovskites, and identification of the best candidates for such processes and such reactions to take place. Also new structures and the enhancement of the structures, both mechanically as well as to better allow the concentrated solar radiation to enter deeper into the structure, and in this way enhance the thermal homogeneity of the structure, as well as the reactions to take place deeper into the structure and exploit the whole mass of and the whole reactor cavity. And finally, introduce concepts of other concepts into the process of solar fuel production that would involve recycling of inert gas, minimization of inert gas, or recycling of inert gas back into the process by using purification components that we would purify, remove the oxygen from the inert gas and allow its reuse, and in this way minimize the consumption of inert gas, as well as the recovery of waste heat. This is a list of references that have been of the research that has been presented in this presentation. And to conclude, we can recognize that there is potential of the solar thermochemical technologies, a great potential, but there are also several challenges that need to be addressed. So we are still talking about low TRL levels, and still we are far from commercializing these technologies, and we need further research back to the fundamentals and to the material level in order to enhance the efficiency of the process and improve the financial viability of such processes. This means redevelopment of materials, redesigning of the solar reactors, and also including in the solar technologies other processes that would improve the process efficiency of the whole process of solar fuel production. So this is it from me. Thank you.
Okay, thank you, Susanna. So last but not least, the next presentation by Nikolaos Tsongidis, also from CERTH. It's going to be about solar hydrothermal liquefaction, a concept that relates directly to one of the pre-designs, one of the 4 pre-designs of SolarHub project. So Nikos.
Thank you for the introduction, George. So, hi everyone, my name is Nikos, or Nikolaos Tsongidis. I'm a collaborating researcher at CERTH. So I have a PhD on solar thermochemical related processes. Mainly I was involved all the past years in thermochemical energy storage applications, but also over the last 5 to 6 years we have been developing hydrothermal liquefaction, and especially its coupling with concentrated solar thermal power. So, as George said, today's presentation will include some details over the concept itself, but also it will be directly connected to one of the SolarHub pre-designs, namely pre-design number 2. So, I will skip all this part, and as already said, regarding the contents, I will begin this presentation with a short introduction with respect to technologies for biofuels and renewable energy production. So some very brief bullets that I will share with you so that you can have an idea over the competitive, or let's say the alternative technologies that are also used for the same purpose. Then I will continue with the hydrothermal liquefaction concept. So this is essentially the conventional HTL. And then I will move on with sharing some details over the solar hydrothermal liquefaction. Then I will continue with the methodology that we follow here at CERTH in our lab. And then I will move on to the pre-design number 2 of SolarHub. And I will share some details regarding the lab scale HTL tests, as well as the design and construction of our pilot scale and the evolution of the pre-design for within the framework of SolarHub. And then I will conclude with some remarks that I will share with you. So some indicative technologies for biofuels production. Of course, some of them are quite well known, some others less well known. All of them are either in early commercial stages, or some of them are also currently at lab scale research. So I will start with, let's say, a descending order of application temperatures. First of all, we can see we have like gasification. We have, in this case, biomass that is converted into syngas through partial oxidation. And in this case, the indicative temperatures of the application of the process application lie generally within 700 degrees C up to 1000 degrees C. Then we have pyrolysis. Pyrolysis is another similar application to hydrothermal technologies, but in this case, the biomass needs to first be processed and dried. So in this case, it's impossible to avoid the energy demanding drying step. Then the biomass is thermally decomposed in the absence of oxygen, and three main products are produced. We have bio-oil, syngas, as well as biochar. And the temperatures are slightly lower than gasification. They range at around 500 degrees C, more or less. Then there is another technology, namely torrefaction. In this case, biomass is thermally treated in an inert atmosphere in order to produce a solid product. The application temperature is quite low, so it ranges within between 200 and 300 degrees C. And last but not least, we have the hydrothermal technologies, including, for instance, hydrothermal liquefaction, in which we will focus on in the next slides. And we also have hydrothermal carbonization, which in this case, biomass is converted into hydrochar, which is a solid fuel in quite low temperatures. So in this case, between 180 and 250 degrees C. The main difference between hydrothermal technologies and, for instance, pyrolysis is the fact that in hydrothermal technologies, we employ water. So in this case, we use highly moist biomass. So some introductory details over the hydrothermal liquefaction concept. Essentially, HTL is a thermochemical process where we convert organic waste into added value products. So in this case, as I already said, the ideal biomass that we use is a biomass that contains a high content of moisture. So in this case, it is an ideal application also for agri-food and agricultural waste. And the treatment takes place at quite medium temperatures, lying between 250 and 500 degrees C, and high temperatures and high pressures between 50 and 250 bar in most cases, but in some cases they can also reach up to 300 bar depending on the type of feedstock. So through this thermochemical conversion, what we do is we first depolymerize our biomass, and then this is repolymerized into different products and byproducts, for which I will share a couple of details now. So in fact, we first have a viscous oil, which is the biofuel or the main product. It is essentially a bio-oil that we receive. This is an intermediate product that usually needs a further treatment in order to be hydrogenated and in order to obtain the end product, which is the biofuel that can be used either for sustainable aviation fuel purposes or also for maritime fuels. We also obtain an aqueous phase, which is rich in phosphates and nitrates. This can also be used for the purposes of irrigation purposes, for instance. We can water plants, and this can also be used as a fertilizer. We also obtain, not always, but depending on the feedstock that we use, we also obtain a solid organic residue, which is a biochar, and this can be used for several different applications. This might include, for example, the addition as a soil fermenter or as an additive to the asphalt mixtures. And of course, there are also other applications that can also lead to applications that need high porosity, and there are several others that are currently under investigation. And finally, we also obtain a gaseous phase. It mainly consists of carbon monoxide, carbon dioxide, but also of methane, among some other compounds. As I've said, we usually don't use some catalyst. We have some reducing gas. This can be either nitrogen or carbon monoxide, even air or hydrogen. It depends on the application and, of course, on the feedstock that we make use of. In our case, we want to keep it as simple as possible. So in this case, the reducing gas can be either nitrogen or air. And we also avoid using catalysts. Of course, some certain types of catalysts, they give us a better result, an improved result when it comes to the efficiency of the HTL process. But as I said, we want to keep it as simple as possible in order to also keep the costs low. And finally, water in the form of moisture is used as a solvent in fact, it is used both as a reactant and as a solvent around its subcritical and supercritical area. So here are some of the main advantages that we can share regarding the hydrothermal liquefaction concept. Of course, most of them apply also to other types of biofuels production technologies. In this case, for HTL, we can say that we managed to diversify the energy sources through the mitigation of fossil fuels use. So in this case, we can ensure energy security for future applications. Then we also have the reduction of greenhouse emissions, especially, of course, through the application that I will share with you more details in the next slides, through the solar coupling that we achieve in our case. Then, of course, because we make use of, essentially, we make use of non-recyclable waste in most cases. These are, let's say, our target group and the feedstock that we prefer in our case. So we managed to have an efficient waste management. And lastly, this kind of applications can lead to local economies promotion, let's say, in terms of fuel sufficiency. So in this case, we managed to have some localized production of biofuels, which can also lead to the sufficiency and self-sufficiency of these areas. So some disadvantages, especially for HTL, the chemistry is quite complex. So this is something that I wanted to stress out. We also have the need to upgrade the products, especially the biofuel product quality through its upgrading and through hydrogenation in order to obtain the final fuels. Then, of course, there are some technical challenges, especially when it comes to the process and reaction control with HTL. We also lack examples of large-scale commercialization. So this is something that is still under investigation in most of the cases. Of course, there are some regulatory barriers which mainly apply to HTL, but not limited only to this concept. And of course, the last thing is that all these technologies need to have public acceptance, which takes time and effort to be achieved. So some of the, in principle, suitable feedstock for HTL. First of all, we have waste. Okay, technically they're waste for the other sectors, but in our case, they're considered as feedstock. In our case, we have agri-food sector. So this means that any kind of waste that comes from the agri-food sector can be used as a feedstock in our case. Then we have several different types of sludge. You have industrial and municipal waste. In this case, it can also consist of different kinds of mixtures, of waste mixtures, but in all cases, we want to avoid, of course, toxic compounds. Then we have food waste, be it from the industry or from, let's say, from restaurants, from kitchens, from houses and stuff. And lastly, we have plastics, both recyclable and non-recyclable ones. Of course, as I also already told you, we tend to prefer non-recyclable plastics in order to produce our biofuel. So these are the main categories. Of course, this can be further expanded through all types of organic materials as well as polymeric materials. And regarding the role of water, as I've already told you, water has a double or even triple role. In this case, it can be used as a solvent, reactant, and catalyst itself, because the rise or the increase of the temperature leads to some characteristics, some parameters that are appropriate in order to depolymerize our feedstock and then, of course, repolymerize it into the biofuel. So the temperature increase leads to its density decrease, the dielectric constant decrease, and the change in its ionization constant. In all these cases and through the application temperatures, we see that these characteristics have a very important role when it comes to the production of our biofuels. And of course, as I said, we in HTL, we avoid the drying of feedstock. On the contrary, we want to achieve as high moisture content as possible, up to 90% of the total mass of our feedstock. So moving on to the introduction of concentrated solar thermal power in our HTL concept. The idea, of course, is to cover the thermal needs of the process using using a concentrated solar power system. So it is as simple as that. The candidate technologies are either linear Fresnel reflectors, LFR, or parabolic trough collectors, PTC, because this is where our temperature range is around. So through our concept, through the idea that I will also show you a couple of details in our methodology that we follow, our concept is ideal for operation of grid and remote areas. So in this case, especially when it comes to the pre-design of number 2 pre-design of SolarHub, the idea is, of course, to be able to treat organic biomass on site, so in the fields and in rural areas. So as also shown, presented earlier by Gökhan, some of the candidate solar technologies here, of course, you can see the whole temperature and operational temperature window that we use. In our case, we use either linear Fresnel reflectors or parabolic trough collectors. So in our case, we have picked parabolic trough collectors because they are more compact and it is quite easy to implement them on the mobile platform that we use for the application of this project. So regarding, the DNI world map, we can see that the area around the Mediterranean, as well as North Africa, South Africa, some areas in the United States and Mexico, as well as in Chile, in China, in MENA countries and Australia, are the ideal places that have a high amount of DNI, of direct normal irradiation, which in these cases exceeds 1,500 kilowatt hours per square meter. So all these areas are, let's say, the ideal areas for the application that we are also working on. So here are some details regarding the HDL developmental path that we follow at CERTH. The idea is that we first start with lab scale testing. So this means that we use our electrically heated steered autoclave reactors in order to perform all the initial screening of the materials, of the feedstocks that we use. Then the idea is that we move on to solar lab scale testing. In this case, we make use of our in-house solar simulator, which is a high flux solar simulator array. In this case, the most promising candidate materials are tested, and then we move on to the semi-pilot scale receiver, which is essentially it is a mobile platform that we have installed to modular parabolic trough collectors, and this is where our reaction takes place. I will share a couple of details in the next few slides. And lastly, of course, the ideal thing and the ideal step is to move on to the commercial scale in order to manage to commercialize our process. So here are some details on our lab scale HDL tests. So the idea is that first, as I told you, we perform all the tests on the electric heater, and then we move on to the solar simulator. So the idea, of course, is to test some parameters, some of the parameters that are tested in the electrically heated system unit, then to also replicate them on the solar simulator. So just to give you an idea, some of the parameters that are tested when it comes to the conventional HDL tests, they include, of course, the reaction temperature, they include the initial pressure that we start our experiments with. Then we also have the retention time of our reaction. Of course, there are other parameters, as I told you, also regarding the use of some catalyst, the atmosphere that the process takes place, as well as other further parameters, also including the ratios between the feedstock and the water, and more that can be tested. In our case, as I told you, we have tried to keep it as simple as possible. I will share a couple of details again in the next few slides regarding our parameters and the testing that we have performed within the framework of SolarHub. So in the next slide are some details regarding our solar simulator. So we have a solar simulator array. Of course, this is not as big as the one that DLR has in Jülich. This is quite small and compact solar simulator. It consists of up to 11 xenon arc lamps. And the idea is that these xenon lamps emit light in a spectra which is very similar to the one of the solar radiation. So in this case, it is quite easy and quite efficient to simulate the conditions that take place on field. And this is, I mean, a quite valuable tool in order, of course, to evaluate lab-scale reactors and, of course, some key components of all the thermochemical related processes. And lastly, the concentration factor that we achieve with this solar simulator can reach up to 4,800 SANS. So moving on to some more details on the lab scale testing, in our electric heater, we use an autoclave reactor, which is a high pressure, high temperature stainless steel reactor. It is a 1.8 liter in volume reactor, so it is quite big in size for the lab scale testing. Of course, we have an electronic controller that we use for the temperature and steering speed regulation, and we use the electric heater, as I told you. Moving on to the solar simulator tests, in this case, we only make use of 4 of our 11 xenon arc lamps, so we have adjusted the array so that we can achieve the quite low temperatures that are demanded by the HTL process. And again, we make use of a 1.8 liter reactor, which was designed and constructed for the purposes of HTL coupling with concentrated solar thermal power. In this image, we can see also in this slide, we can see some images of the testing that is currently taking place in our solar simulator. And then probably the most interesting part is the semi-pilot mobile HTL platform. So this is something that was designed and constructed in-house. We have 2 modular 6 liter tubular reactors. In this case, you can see that they're, let's say, separated. Each of them has its unique sun tracking system. We employ parabolic troughs as the heating means, and we have a heat transfer fluid that surrounds the reactor in order, of course, to achieve the optimum heat conductivity. So far, we have successfully managed to achieve the proof of concept operation, and the experimental campaign is underway. Of course, some modifications and some actions will be also taken into account also for the needs of SolarHub pre-design. So this is something that will be tested over the next months. So some things and some details over the SolarHub pre-design number 2. So the idea in this case is to have 2 main parts. So the first part is the HTL reactor part, and the second part is the thermal energy storage part. So in this case, we want to prolong the operation of the HTL reaction and make it run, if possible, round the clock. This is something that is currently under modeling tests and under modeling consideration. In this case, what we see here is that the idea is that we will be making use of one of the 2 modular parabolic trough collectors with the HTL reactor during the day. So this will be heated during the day directly with the concentrated solar thermal power. And then we will also have a secondary PTC in which we will have, it will be heated during the day. Then this heat transfer fluid that will be running through the reactor tube will be pumped into a packed bed thermal energy storage tank. And in this case, we will be heating the particles that are immobilized within the packed bed tank. And through this, when we are in off-sun hours or during the night or in cloudy days, the idea is that these heated, these particles will emit the heat that they have stored in order to cover the needs of the HTL reaction when, of course, we cannot reach the desired temperatures with, let's say, direct irradiation of the HTL reactor. So in this case, the idea is, as I've already stressed out, the idea is to prolong the operation window, if possible, even round the clock. So regarding the first part, which is highlighted in red now, the idea is that we have tested 2 different kinds of feedstocks. They both come from the agri-food sector. We have a partner in SolarHub project called Venus Growers. In fact, they are producing, they are treating peats and the waste that they obtain are either pit skins or pit stones. So in our case, we have tested both pit skins and pit stones. The idea is to make it as simple as possible, as already stressed out. So we use nitrogen as reducing gas. The temperature window between the several different experiments that we have performed is between 280 and 350 degrees C. We have employed two different initial pressures, either 1 or 20 bar, to have a steady residence time of 30 minutes, and the water to waste ratio is kept constant at 90 to 80 weight percent. And for the cases that we need some extra solvent in order to separate the biocrude, the bio-oil that we obtain from the aqueous phase, we use either dichloromethane or ethyl acetate. And of course, these solvents are retrieved and reused for our application. So in total, the idea was to perform 16 experiments for both feedstocks using conventional heating means. And in this slide, we can see the most promising results for both feedstocks. So we have used a quite simplistic equation in order to calculate the bio-oil yield. So in this case, we calculate the yield through the ratio of the weight of bio-oil over the weight of dried feedstock. And this is a very simple and efficient way in order to measure the bio-oil yield. So the best results that were obtained were for the pit stones, where we applied an initial pressure of 20 bar and 350 degrees C as the reaction temperature. And we have also used ethyl acetate in order to separate the aqueous phase from the bio-oil. And on the right-hand side, you can see some indicative images of how the aqueous phase, which is a bit yellowish, I would call it, is separated from the black viscous biofuel that we obtain. So we have also performed some characterization tests in order to be sure that the quality that we obtain either from the feedstocks that we use or from the products that we obtain is within the desired window that is performed and is evident from the literature itself. We see here we have performed some preliminary characterization when it comes to first to the feedstock. So, for example, we have thermogravimetric analysis for both pit skins and pit stones. We see that the moisture evaporation takes place in the window of 40 to 140 degrees C. Of course, in the case of pit skins, because they're more moist, we see that the weight change is quite significant. Then we have the next temperature zone between 140 and 240 degrees C, which is the volatile content evaporation area. In this case, we see that for the pit stones, this is the temperature window where the weight decrease begins. So this is evident of the decomposition of heavy organics. So in this case, the pit stones mainly consist of heavy organics, while we see a more normal distribution for the case of the pit skins. And of course, above 500, 550 degrees C, we see that we have a negligible weight change, which also means that the presence of inorganics is very limited, if not close to zero. We have also performed FTIR tests in order to define the main compound groups. We have aliphatic amines and aldehydes, amino acids, methylene, alkenes, and ketones. This is the case for most of the biomass coming from the agri-food sector. Then, this is quite interesting, I would say, is the measurement of the high heating value of the products. So when we compare the high heating value of the products to that of the feedstock, we see that in all cases, we have managed to observe a significant HHV increase. So in this case, it ranges between 60%, which is in the case of pit skins, and can reach up to 5 times, which is in the case of the pit stones. So in the case of pit stones, we see that the raw material had a higher heating value of approximately 7 megajoules per kilogram, and this managed to reach up to 35 megajoules per kilogram. So this is a quite significant increase in the HHV of the pitch stones. But again, the same applies to the pitch skins, because we see that the HHV has increased by almost 60% in both cases. So in the case that the biofuel heating value exceeds 30 megajoules per kilogram, is a very good sign that this can be further upgraded into biofuels that can be used either for actually for several different applications. And also regarding the hydrogen over carbon ratio, we see that the results that we obtain are in the range of 0.12 to 0.13, which are very close to the literature values for similar type of agri-food. And lastly, the inorganic impurities, as also observed by the TGA, as well as the toxic compounds, are almost non-existent. The second part is the thermal energy storage part. This is mainly covered by our colleagues from UNAM, from Turkey. And the idea so far is to create a model, a 3D model of the proposed cylindrical geometry. So in this case, we can see some images coming from COMSOL, and we can also see some of the results that our colleagues have obtained through very numerical models. So the idea in this case is the heat transfer to take place in packed bed reactors and packed bed tanks. And they also make use of different types of filling materials. So these filling materials, they can be some different grades. As we can see here, they have tested olivine sand, carbo HSP, which is a bauxite-based material, and they also use some types of olivine. So in this case, they have obtained the temperature that can be reached and that can be stored within the particles. But of course, this is a research that is still taking place and is currently an active research. And also, this will be included in the results of SolarHub redesign number 2. So some of the main conclusions that so far can be obtained through the application that we've been developing in our case. We can see that solar hydrothermal liquefaction is indeed an efficient way of treating residual biomass. The idea is that we obtain an intermediate biofuel, which is our main product in this case. This can be either further upgraded into a biofuel, which is an end product, let's say, but can also be tested and used in some applications, even like in marine or some other applications, and some other applications that do not demand a really sophisticated biofuel to be used. So this can also be used in the agri-food sector as well. But of course, this is something that also needs some further quality testing that will take place within or right after the SolarHub project. And of course, we also obtain some useful byproducts that they include the aqueous phase, the biochar, as well as the gaseous phase that can also be combusted. So currently, the testing of pre-design number 2 is at lab scale. The idea is that till the end of SolarHub, till the end of the respective work package, some semi-pilot scale testing will take place in the mobile platform at CERTH, as well as at the parabolic trough collectors that UNAM have in their facilities. We see that we have managed to achieve a bio-oil yield that exceeds 60%, which is quite important. And based on our previous and past experience, we are confident that this bio-oil yield can be further increased when we will be using the solar facilities like in our solar simulator. Lastly, the PTC model is currently under development by UNAM. And as I said, the idea is, of course, to couple it with the thermal energy storage model and use it in the analysis that will take place in terms of sizing. And as a closing remark, the ending TRL of our pre-design is aimed to reach up to 5, but of course, some of the components can also be closer to TRL 6. So the idea is that with the acceleration program, this will be this will be a great chance to even further promote our pre-design to higher TRLs and avoid, let's say, the valley of death of the pre-designs and the technologies themselves. So with that being said, the main contact for the pre-design number 2 is Dr. Onur Taylan from METU and O2 UNAM, as well as myself on behalf of CERTH. So thank you so much for your attention.
Okay, very good. Thank you so much, Nikos, for this elaborate presentation. If I may personally say, I believe that this last presentation is a good example on how we can, let's say, exploit solar energy, solar thermal energy to drive chemical reactions and produce useful products, while at the same time we can address in a pretty straightforward way a concept which is clearly in the scope of circular economy. This is also very important. So let's say you can hit 2 birds or even more with one strike. Let's see in the chat. Okay, no, the comment about connection. I think we are right on time. It's 1 minute after 1 o'clock. If you have any questions, please speak up now. I hope you found this training session useful. Some examples, the general context and some examples of how medium to high temperature solar heat can be exploited for industrial relevant applications. Clearly, there is some work that needs to be done, some research to be carried out, some more achievements to be made. But I think that solar thermal is really promising, and it has its niche areas that can be applicable and can provide, as you saw, solutions to certain problems and challenges of industrial importance, and of course always towards aiming at a low carbon footprint. So I can see no questions or comments. And with this, I would like to thank you. Thank you very much for participating. See you next time. I believe you all have access to the schedule of the training and mentoring events of SolarHub, our accelerator, which is fully deployed. Thank you very much. See you next time.
There's a question, George.
Sorry.
Actually, some participant raised his hand.
Okay. Sorry about that. Harsetti, if I pronounce well the name, you have raised your hand. You want to ask a question?
Yes.
Yeah.
So I have a question for the first speaker, and they are using the solar panel for generation of heat by using the dispersed light. I'm based in India, and we are also working on PV module solar energy using nanotechnology. So we do coatings, nano coatings on the glass surface of the PV modules, thereby increasing the surface area. So we mimic a microstructure which is similar to Amazon raintree forest. So when light falls on it, it doesn't get reflected, it gets refracted. And because of the thickness is 0.4 micron, much thinner than here, that light is transmitted to underneath silica. So when silica gets more light, it generates more energy and more power. And secondly, because of the unique microstructure, very pointed tips, anything which is falling on the coated surface, like dust, oil, or bird droppings, etc., they don't flatten out, they don't stick with a single point of contact. So you can easily clean it. So my question is that, is it possible to collaborate with certain companies here, because the two technologies can be merged with better results. That's just an idea.
Yes, this is a good idea, I think, although not in the mirrors part of the solar thermal installation, but maybe it's gonna be more useful on the receiver part to somehow increase absorptivity and all that. But Gökhan, if you wanna further comment on this, I think in principle it is a good idea. Of course, further discussions will need to be carried out in order to see if this is really a potential collaboration area. But it often happens that between PV and solar thermal, there are common aspects and common components, secondary components that can be exploited by both technologies.
Yeah, I would agree there. So maybe I just share my contacts, and if you have a short portfolio or some few slides summarizing what you work on, then I would be happy to look into that. Is that fine?
Yeah, sure, absolutely. I can also share some of the commercial small-scale projects we have done across India. So from western part where there is desert to coastal areas, and northern part where is snow, to down south where is a lot of rains, with different panel manufacturers, different brands, different makes. So we have done quite a lot of projects. We already have a patent in India, have been endorsed by the government of India as a innovation made in India technology. So would be happy to share with you, and look forward to collaborating to increase the efficiency of solar panels so that everybody can use it and the world becomes more cleaner and greener.
Yeah, all right. Sounds good. Yeah.
That's the goal, actually. So,
Yes.
Celine, I think the contacts are available. I mean, you.
Yes, I will
Okay.
introduce you each other maybe in an email exchange so you can take it from the rest. We also recorded the event and to be only shared with this ignition participants. But for the third part, I will upload them on the YouTube, and we can then make it also public, if that's fine with you, because DLR keeps it private.
Okay, yes.
Okay. Let's discuss it also.
But I mean, Gökhan already wrote his email address in the Q&A section. But in any case, Celine, yourself, you also have access to all contact details, and you can easily put Gökhan and our external participant, thank you very much, to discuss about it.
Of course.
Okay, thanks. Let's thank all our speakers today for their valuable time and their really useful and very interesting presentations. Thank you, Gökhan. Thank you, Matthias. Thank you, Susanna. Thank you, Nikos. Thanks, everybody. I think we can now conclude. Have a nice day.
Thank you too. Have a nice day.
Thank you, George. Have a nice day.
Bye.
Bye.